The James Webb Space Telescope, JWST, stands out as the premier global observatory in the ever-evolving and cutting-edge field of space science and astronomy. As the most advanced and sophisticated space-based observatory humanity has ever launched, it represents the pinnacle of decades of engineering innovation, scientific curiosity, and international collaboration. Its mission transcends mere observation. It is committed to investigating the vast array of enigmas surrounding not just the celestial bodies within our own solar system, but also distant worlds orbiting remote and often dim stars in far-flung regions of the galaxy. In addition to peering into the depths of space, it also allows scientists to delve into the complex, interwoven structures of our universe, seeking answers to age-old questions about cosmic origins, stellar evolution, planetary formation, and perhaps even the beginnings of life itself. Through this remarkable technological achievement, researchers hope to better understand the physical laws that govern space-time and to explore the unique and significant role humanity may play within the incomprehensibly vast and mysterious universe. In a remarkable and recent initiative, a cohort of scientists decided to utilize the unparalleled capabilities of the Webb telescope by directing its gaze toward a particular star located approximately 120 light-years away from our solar system. This celestial body, though distant by human standards, lies within observational range thanks to JWST's powerful infrared sensitivity. What unfolded during this mission astonished astronomers around the world. The Super Telescope, so named because of its enhanced sensitivity and resolution compared to its predecessor, the Hubble Space Telescope, managed to capture compelling and direct evidence for the presence of carbon-based molecules in the atmosphere of what is believed to be an ocean world, a type of exoplanet located far beyond the confines of our own planetary neighborhood. This detection of complex carbon compounds in such an environment has baffled the global astronomical community and prompted a flurry of research, debate, and excitement. How exactly is this surprising and extraordinary revelation possible? The answer lies in the advanced spectroscopic tools onboard JWST, which allow it to analyze light filtered through the atmosphere of distant exoplanets as they pass in front of their parent stars. This innovative observational technique provides scientists with the ability to decipher the chemical makeup of exoplanetary atmospheres with an unprecedented degree of detail. The discovery has offered a rare and fascinating glimpse into a planet that appears to differ in significant ways from any known planet within our solar system, raising profound and tantalizing questions about the possibility of a habitable world existing in a completely different corner of the galaxy. Could this planet support life? What kind of environment exists on its surface or beneath its atmospheric layers? The answers to such questions may eventually reshape how we define habitability and life itself. We invite you to join us on this exciting scientific journey to uncover and share more intricate details about this mysterious exoplanet and its implications for our understanding of planetary systems. If you are passionate about space exploration and interested in staying up to date with groundbreaking news about the universe and its dynamic phenomena, please consider subscribing to our channel. Be sure to like this video to support our content, share it so others can learn as well, and turn on the notification bell to never miss an update. Specifically, NASA's James Webb Space Telescope has made a groundbreaking and highly relevant discovery concerning an exoplanet known as K2-18b. This intriguing celestial body has a mass roughly 8.6 times greater than that of Earth, placing it in the category of super-Earths or mini-Neptunes, types of planets that do not exist within our own solar system, but are commonly found throughout the galaxy. The significance of this discovery lies in the identification of crucial carbon-based compounds such as methane, CH4, and carbon dioxide, CO2, within the atmosphere of K2-18b. These compounds are often associated with biological processes and can indicate the presence of a planet's internal geochemical cycles or even primitive life-supporting conditions under certain circumstances. Webb's discovery builds upon and expands earlier research that had already suggested the possibility of K2-18b being a planet with characteristics potentially conducive to the emergence or support of life. Observations imply that this exoplanet possesses a thick hydrogen-rich atmosphere and a surface potentially covered by a vast liquid ocean. This combination is considered by astrobiologists to be among the most favorable for habitability outside of Earth-like conditions. The very first serious attempt to explore the atmospheric properties of this exoplanet in what astronomers refer to as the habitable zone, a region around a star where conditions are suitable for liquid water, was conducted using NASA's Hubble Space Telescope. That mission alone brought significant insight, but it is the Webb telescope that has now transformed our understanding of the system, thanks to its improved ability to gather and analyze infrared data. It's important to emphasize that K218b resides at a distance of approximately 120 light-years from Earth, within the constellation Leo. It orbits a relatively cool dwarf star known as K218, which emits far less radiation than our Sun. Despite its cooler nature, K218 provides enough warmth to keep its nearby planets within a potentially life-supporting temperature range. This is a defining feature of the so-called habitable zone, a concept fundamental to the search for extraterrestrial life. Planets like K218b, which fall between the size of Earth and Neptune, are of particular interest to astronomers because they belong to a relatively rare category that appears largely absent from our own solar system. As a result, these types of worlds are less well understood, yet they could very well be the most common habitable environments in the Milky Way. What makes K218b so especially intriguing is the suggestion, based on observed atmospheric signatures, that it might harbor not only a significant abundance of carbon compounds, but also a thick hydrogen-dominated atmosphere. Some planetary scientists and exoplanet researchers believe that such a composition could result in a temperate surface environment, shielded from the harsh conditions of space and conducive to biochemical processes. The presence of methane and carbon dioxide is viewed as further support for the theory that this exoplanet may host an ocean beneath its outer atmospheric shell. Moreover, there have been early indications pointing toward the possible presence of a compound known as dimethyl sulfide, DMS. This molecule is particularly significant because, on Earth, it is produced almost exclusively by life, primarily through phytoplankton activity in oceanic ecosystems. The detection of DMS in an exoplanet's atmosphere, even tentatively, could represent one of the most promising biosignatures ever found beyond Earth. However, the inference of DMS in K218b's atmosphere remains tentative. The data supporting its existence are not yet robust enough to claim definitive detection, and further observational campaigns are necessary. As more refined data becomes available through the telescope network and additional instruments on the JWST, scientists hope to verify whether this compound truly exists in significant quantities in the planet's atmosphere. Should that confirmation come, it would be a monumental step forward in the ongoing search for extraterrestrial life. An astronomer from the University of Cambridge explained that while the presence of carbon compounds and the planet's location within the habitable zone are both promising indicators, they do not, in and of themselves, confirm that K218b is capable of supporting life. One complicating factor is the planet's large size. Its radius is approximately 2.6 times that of Earth. This suggests that it may possess a dense, high-pressure mantle composed of ice or other exotic materials beneath its atmosphere, much like what we observe in Neptune-like planets. Although it also has a relatively thinner hydrogen atmosphere and possibly an oceanic surface, the physical conditions there could be far more extreme and inhospitable than initially anticipated. There is the possibility that the presumed ocean is not in a liquid state or may be too chemically hostile to allow life, as we know it, to thrive. Despite these challenges, researchers have managed to obtain the most detailed spectrum to date of a habitable zone sub-Neptune-type exoplanet, using JWST's advanced instruments. The achievement allowed them to identify multiple molecular components within K218b's atmosphere and offered clues to the planet's physical and chemical structure. One member of the team from Cardiff University detailed how this achievement was made possible by examining the light emitted from K218's host star as it passed through the atmosphere of K218b. This technique is especially useful for studying what are known as transiting exoplanets, planets that move in front of their host stars from our vantage point, causing a slight dimming in brightness. This dip in brightness enables telescopes to capture starlight that has been filtered through the planet's atmosphere, carrying with it crucial chemical information. This innovative method allows researchers to estimate the quantities and types of gases present in exoplanetary atmospheres. The JWST team now plans to continue their investigation by focusing on the telescope's mid-infrared spectral capabilities, which will not only help confirm their initial findings, but also provide valuable insights into the climate, temperature gradients, and surface conditions of K2-18b. Their ultimate and long-term objective is to search for signs of life on potentially habitable exoplanets, a pursuit that could completely revolutionize our understanding of biology, chemistry, and the universe as a whole. In addition to these discoveries, the James Webb Telescope has also revealed astonishing data from even more distant parts of the cosmos. In one instance, astronomers detected complex organic molecules, resembling smoke or atmospheric smog, in a distant galaxy. This detection marks the earliest known appearance of such molecules in the universe and suggests that the fundamental building blocks of life may have formed far earlier than previously believed. The molecules in question, called aromatic hydrocarbons, are typically found in substances like crude oil or coal on Earth and are also prominent in air pollution. These aren't simple molecules like water or carbon dioxide. Instead, they are large and complex, containing dozens or even hundreds of atoms. Their detection in a galaxy that formed when the universe was only 10% of its current age challenges many established assumptions in cosmology. The fact that the universe was able to synthesize such complex compounds just 1.5 billion years after the Big Bang is a testament to the power of natural cosmic processes. The light from this ancient galaxy began traveling toward us billions of years ago, and now, thanks to the capabilities of the Webb telescope, we are able to observe it and glean information about the early stages of galaxy formation, chemical synthesis, and perhaps even the precursors to life. These molecules were found in a galaxy already as massive as the Milky Way and enriched with carbon and oxygen, demonstrating that stellar and galactic evolution may have occurred much more rapidly than previously thought. As humanity continues to expand its reach into the cosmos, armed with instruments like the James Webb Space Telescope and fueled by a relentless thirst for discovery, we are constantly reminded of how small and precious our place in the universe is. Each scientific breakthrough not only enhances our knowledge, but also pushes us to reevaluate long-held beliefs. With every new data point, we get one step closer to unraveling the mysteries scattered among the stars. Stay with us as we journey deeper into the unknown, because it's only a matter of time before the universe yields even more secrets and shine.